So, welcome to the second class. So, I did get the video from Wednesday up on this morning. I don't think anyone's actually going to go back and review that one. But it is there if you need it. Today's lecture will be posted basically immediately after. Immediately after this, I also posted a little thing for, since we're not having a quiz this week, just a little, send me a picture and tell me a little something interesting about yourself so I can hope to recognize names and faces a little better. And so that shouldn't take any time, just like a couple sentences and a picture. It doesn't have to be a formal picture or anything. Okay. So for the first part, we're sort of doing, before we get into aluminum, we're going to spend a couple lectures hitting some fundamentals, right? And I want to start with, I titled this The Structure of Real Metals, right? And mostly it's about grains and grain boundaries, right? Remember, metals are not homogeneous, right? That's the whole point of this class is connecting microstructure to processing and properties. When we're in the specific alloys, we're going to be talking a lot about phases, secondary phases and phase transformations, right? And aluminums will be our archetype system for that, because it's not a pure aluminum is nominally a single phase. It doesn't go through any temperature dependent phase transformations. But with alloying, you have a whole bunch of different transformations. And so we'll use aluminum as our case study to talk about thermodynamically how these phase transformations happen and what effect they have on strength. And then when we get to steel, we can talk about the specifics of that system, the iron-carbon system, right? Without everything basically becomes transferable. Now we just have the added complexity of a temperature-dependent phase transformation. Right? We have a FCC, BCC transformation in pure iron. What I want to talk about over the next couple lectures are things that are common across the entire spectrum. Right? For the most part, the metals that we're interested in, with the exception of some of the superalloys that we'll talk about at the end of the system, are used in a polycrystalline state, right? Everyone has done some metallography. Everyone's seen a grain structure. You're laughing because, right? Right, this shouldn't be a surprising picture to anyone here. This is zirconium, and this isn't etched. This is instead a polarized light microscope, right? So where's the contrast coming from? Why do these different grains have different contrast? Yeah? So orientations, particularly the C-axis orientation, right? Zirconium is what crystal structure? HCP, right? It's a group 4 metal like titanium and hafnium. So it's HCP, and the contrast here is coming from the C-axis orientation. And I said it's not etched. In fact, it is etched. Right? But we can see some grain boundaries are very dark and thick. Others are very thin. And others, oh, Google's telling me that's a scam. Scam likely. That's always a good thing to come up on caller ID. Others are essentially absent. Right? Why would some grain boundaries etch differently than others? Yeah.
Segregation that can happen with grain boundaries and the grain boundary composition.
That could be, but it's not the case here because this is this is pure zirconium. Right? Yeah, Eddie. Could be. Misorientation is part of it, right? It's the grain boundary, the character of the grain boundary, right? How is that grain boundary constructed, right? If I take two crystals of two different orientations and stick them together, there's going to be some boundaries that have a higher energy than others, right? Some of them that are more stable than others, right? What else can we learn by just looking at this? Texture, we'll get there. You can't necessarily tell texture. You can tell part of texture. You can tell that, in general, I see no real preference between light grains and dark grains. So that means there's no preferential C-axis orientations in my sample. But we don't have full texture information here. Right, what else?
Size of the grains.
Size of the grains, right? The grains are not perfectly uniform with respect to size. We see a couple other things. What's sort of a common feature of all the grain boundaries? Triple points, right? So we see all of these triple points, right? What's this approximate angle here? Right? They all meet in triple points. Why don't we see very many 4? Here's one. Right? Why is 3 much more common than 4? Right? That'll actually be one of the questions to ponder that you'll get this week, because we'll talk about surface tension of a grain boundary. Right? But there's a whole lot that we can see here. How are the grain boundaries approximately straight, or are they bent and tortuous? They're relatively straight, right? So thinking about what we talked about on Wednesday, why do we have mostly straight grains? Right? We talked about Gibbs-Thompson and how curvature affects mobility. Right? That was one of those rules of thumb. Right? So these straight boundaries are going to have much less mobility under annealing. Right? The highly curved ones moved and are gone. Our systems evolved. All right, so there's a lot we can see from this. There's one other thing that jumps out at me. Does this look like a deformed sample or a well-annealed sample? Right? How do we know it's well-annealed? The grains are roughly equiaxed, and I don't see any real contrast here. What happens in a polycrystal when you deform it? Grains rotate, but anytime you have a strain gradient, you have a accompanying orientation change, right? And so I don't see the grains all appear to have a homogeneous C-axis orientation, right? So whenever we look at these things, look at the clues that the micrograph is telling us. Okay, so if we're going to start with grain structure, we need to think about the grain boundary. And for a small misorientation angle between two grains, we can model the grain boundary itself as essentially an array of edge dislocations. All right, so here we're taking these and we're rotating about the 001 crystallographic direction. We get a nice vertical array of dislocations. The greater the degree of this inclination becomes, the closer these edge dislocations have to be, right? We need more degrees of freedom in our system. And it's not too hard to derive, if you think about it, that we can think about the angle of our simple tilt boundary. If we know the Berger's vector of our dislocations, we can easily calculate the distance between the defects that we need, right? And it's basically just setting up a nice little triangle, right? Okay, so this is great for low angle boundaries, but there is really no simple model for high angle grain boundary structures, right? I think that was one of the first and most important aspects that atomistic simulations of metals really began to get at, is what do grain boundaries actually potentially look like? And as we'll see, they've only really explored a very small amount of space of the potential configurations of grain boundaries because of the number of degrees of freedom that they have. So here we can see, this is a etching of a high purity magnesium specimen. And these we have actually a very special grain structure. These are a twist. Grains are aligned, a special twist boundary along the basal, the 100 direction. So the basal planes are rotated with respect to each other at the interface. And you can actually see the edge pits corresponding to the edge dislocation, the dislocations that make up this intersection. Right? When you start to combine tilt and twist, I should be careful, right? This is a twist. These are actually not edge dislocations. They have screw character to them. But that's not really important for what we want to do. The structure becomes much more complicated as you add tilt and twist character here. Right? You can see that the dislocation structures at the grain boundary are not simple arrays of edge or arrays of screw dislocations. Right? The structure of the grain boundary rapidly becomes very complicated. And this has been deformed plastically, so we see arrays, networks of dislocations piling up at the interface there. And so this is pretty cool, right? And if we think about it, it wasn't all that long ago. In the 1950s, up until the 1950s, there were still debates about whether dislocations were real or whether they were a mathematical convenience to explain some things about metals, right? It wasn't until the TEM came around and people actually saw dislocations that it was settled, right? I have some physical metallurgy books from Sir Alan Cottrell from the 40s, and it has things that says, if the dislocation theory is proven correct, right? So it wasn't really all that long ago. And without a picture of dislocations, grain boundaries sort of don't make any sense, right? I mean, we talk about crystals, but why should they have all these different sort of character? So important things to keep in mind, right? As the angle of the grain boundary is increased, the dislocation structure becomes more complex. So here we have a 10.5 degrees symmetric. And by symmetric, we mean that the half angle, the misorientation of the lattice on each side is the same, right? So this is 5.25 degrees misoriented from the grain boundary, line. Yeah. Yeah.
I was just wondering about steel and how far away from the boundary.
Okay, so scale on this is like I'm breaking like one of the biggest rules here, right? I'm showing micrographs without a scale bar. That's just like a huge no-no. So this structure here, right? This is a deformed specimen. So you would expect to see a dislocation structure like this sort of throughout, right? What I really was just wanted to highlight was here's the grain boundary, right? And you can see that there's no simple picture here, right? You don't see anything that resembles this nice spacing. In fact, you see the spacing of the dislocations on this side of the grain boundary is quite different than what you see here, right? And these are the way these dislocations interact with the grain boundary is quite different in both of these grains. And so the main idea here is just that the structure is very complicated, even though it's a low angle grain boundary, because it's not a nice, clean, symmetric tilt or twist, the dislocation structure is pretty complicated. Right, and that's sort of what I wanted to show here as well, is that when you have a nice symmetric grain boundary structure, right, you can see here we have these dislocations. These are sometimes colloquially called kite structures, right, because they kind of look like kite on a string. But as we increase the misorientation, the structure becomes more complex. These become closer. Now, because this is a special symmetric tilt structure, right, even though this is going up to 36.9 degrees, close to 37 degrees, we still have a nice cool structure. But if you do the same thing and you make it not symmetric, so now this is 26 and 10 over here, right, the grain boundary structure isn't clean. You can't really describe it anymore, even though it's just a pure tilt. Now, if you add a twist character to that as well, it all goes to hell, basically, right? And here's just another sort of example of an asymmetric tilt. You can play with this with some graph paper and put this out on your own. You can see that the dislocations that make this up don't all have the same line direction. They don't all have, right? They're not all, it's not an array of the same dislocations, right? Once you get into a asymmetric condition, you need to, the dislocation structure stops being regular and needs to have some different characters. Symmetric twists are really pretty because what happens is you get relaxation, so you have essentially regions where things are aligned with these periodic arrays of screw dislocations that come up, and they make some really neat patterns, pure symmetric twist boundaries. That the nature of these dislocations, nature of these arrays of screw dislocations becomes pretty cool. And until you spend some time looking at these, it's not immediately clear what the angle of rotation actually is, because you end up with regions where your atomic planes line up separated where your atoms line up in a matching lattice, and regions where they don't, right? But if you look, you can see this angle here, right? The overall lattice is actually rotated by this angle here divided by 2. So that's a little bit of the structure of grain boundaries. If we want to define it a little bit more, we said the grain boundary is where 2 grains with a different crystal orientation meet together. So if we're going to define the grain boundary a little more carefully for an arbitrary case, other than some special ones, we need to define what a crystal orientation actually means, right? So we have a lattice. We have 3 lattice vectors, A, B, and C. And it doesn't matter if this is cubic or not. We can always define 3 Cartesian vectors that define some basis for our crystal, even if we have a hexagonal lattice or a monoclinic or whatever. The way we define an orientation is a mapping between the lattice vectors that define the local crystallographic coordinate frame, our local crystallographic basis vectors, and some arbitrarily chosen sample reference frame, right? So in this case, the natural sample reference frame is the x, y, and z coordinate of our sample frame, right? Whenever we measure these, we're doing EBSD, electron backscatter diffraction. We use the microscope coordinate frame, right? The normal direction to our sample, our polished surface, right? Then we have two directions in the plane. So we always define orientations as a mapping between what's there and some reference. Now the nice thing about that is, as long as we define our reference and we're consistent about it, no matter what reference we pick, our misorientation between two orientations is always the same, right? So we can define a misorientation as the rotation needed to bring this crystallographic frame into coincidence with this set of lattice vectors. Right? So how many parameters, this is a rotation in 3D, how many parameters do we need to define a 3D rotation? What? 3, right? Right? We typically do this with Euler angles. We can also do it by rotation matrices, rotatio matrices. Right? Should be N. Rotation matrices, which are a 3x3 matrix, but it turns out that only you can define all the other components in terms of three of them. Quaternions, the angle, the rotation angle, and the axis is probably the easiest way to come up with the 3, right? So I can define any three-dimensional rotation by a vector, a unit vector that defines the rotation axis, and the rotation about it. Well, a vector in 3 dimensions needs 3 numbers, right? X, Y, and Z components of vector, but it's a unit vector. So that means I know that its length has to be 1. So I need 2 numbers to define my rotation axis, and then I need another number, the rotation angle, to define how far I've gone about it. Right? So three degrees of freedom, 3 parameters for a 3-dimensional rotation. All right. I said misorientations are from one crystal to the other. Right? So this is actually kind of a really important plot. Right? Has anyone seen this before? The McKenzie distribution, right? This is if I have a polycrystal with no texture, and I randomly pick one orientation and another, and I calculate their misorientation between them, and I do that a huge amount of times. It's not, my misorientation isn't uniform. I'm much more likely to have a high degree of misorientation than a low. Why is this stop at 63 degrees? Why doesn't it go out to 90 degrees, right? I can have cubes, right? It's pretty easy if I have 2 cubes to rotate one 90 degrees relative to the other. What happens with crystals? If I have a cubic crystal and I rotate it 90 degrees on a cube face? It's the same, right? It's a symmetry element. So if you take all the symmetric equivalents into account, the maximum misorientation you can have for cubic is 63, right? There's only one possible way you can have that. So you have a very low probability of actually ever seeing it. Most of what this tells me is most of the time, if I pick 2 random grains in a polycrystal, well annealed without any texture, there's going to be about a 45-degree misorientation between those 2 lattices. High angle grain boundaries are much more common than low angle grain boundaries. It's kind of an entropy argument, right? I have much more ways of just arranging those. So people sometimes will calculate the deviation from a McKenzie distribution of their samples to show not just that there's a texture in my sample, but also, is there any preference for a misorientation? right? I can have a sample that is completely random. There's no preference for a particular orientation to appear, right? But my grains are still, my misorientation distribution is highly deviated from this. You could say grain A always likes to be next to grain B, even though there's the correct population of grains A and B in my system. It's a little confusing. This is a whole area of metallurgy that's really come into prominence over the last 10 years called grain boundary engineering, right? So you're trying to find networks of grain boundaries that give you much better properties than the networks of grain boundaries you get from the McKenzie distribution. So for a general grain boundary, we said the misorientation, we need 3 parameters, right? But we need 5 parameters to define a grain boundary. Where do those other 2 parameters come from? The grain boundary plane, right? So if I have 2 grains, A and B, right, their lattice is fixed, right? So my misorientation is constant. But if I have a grain boundary plane that's like this versus a grain boundary plane that's like this, even though I have the same orientations on either side, that grain boundary is going to have a very different energy. There needs to be a very different defect structure because we're cutting through those planes and stitching them together at a different angle, right? So the 5 parameters for the grain boundary to really define a grain boundary comes from the misorientation between the 2 and the inclination of the plane, right? So we define the inclination of the plane by another unit vector, grain boundary plane normal, because it's a unit vector, it's 2 numbers that we need, right? So that means the space of potential grain boundaries is huge, right? So if you look in the literature and people talk about the structure of grain boundaries from atomistic calculations, they typically do symmetric tilts and symmetric twists, right? And the vast majority of this space hasn't been filled. You can imagine, just do a little bit of calculation to think about this. If you have a unit vector that varies every 5 degrees for your grain boundary plane, right? So if you think about if you take a sphere and you do that, how many points that is on a sphere, right? And then you think about the 3-dimensional misorientations, right? So now you would have that again, that same number, times 5. Every one of those would be multiplied by a 5-degree rotation about that, right? You end up with like a very coarse sampling of the space. Ends up being like 360,000 possible grain boundary configurations for cubic, right? If you have a lower symmetry metal, now say you have interfaces of 2 different metals, like FCC and a secondary phase, which has tetragonal or monoclinic crystal structure. That space becomes astronomical, right? So we can't really explore this all. This is a huge, huge open area, right? And this is just another alternate way of parameterizing, describing the degrees of freedom you have. Right? You've got a tilt, a twist, where you can think about tilt this way, and a twist combined. If you put that together, you have 5 ways. Just an alternate way of describing it. Okay. So we know we have all these grain boundaries in there. Grain boundaries, we say, are made up of dislocations. Right? One of my rules of thumb was the stress field around a dislocation. Right? A dislocation has a long-range stress field, right? you've perturbed atoms from their equilibrium position, right? So all these atoms of strain, they're stretched from their ideal position that they'd like to be in. So a grain boundary has a long-range stress associated with it of GB over R. And so if grain boundaries are made up of dislocations, it's natural to assume that grain boundaries also exhibit a long-range stress field. Right? That makes sense. The superposition of a whole bunch of stress fields is also a stress field. Unfortunately, I guess maybe fortunately, but we don't see that, right? When people cut out TEM samples, they don't bend. TEM foils. When you take a well-annealed metallographic sample and you section it on the saw, it doesn't spring when you finish cutting all the way through, right? It can because of residual stresses and other things from thermal shock or whatever. But if it's a well-annealed cubic metal, that never happens, right? When you did your characterization course and you looked at X-ray diffraction, right? Stress fields are one of the things that strain fields are one of the things that cause peak broadening. But in a well-annealed metal, you don't see any peak broadening. So all of these things suggest that no, the grain boundaries don't actually, in fact, have a stress field associated with them, right? So sort of how does that work out? And it's actually not that hard to work out, right? So here, I'm not going to derive it, but this is the stress field for an edge dislocation. Hopefully this isn't the first time, right? I'm sure the welding students, this is probably the first time you've seen this. Don't worry, you don't have to memorize this, right? But this is the stress field that you get around a edge dislocation, right? And it's kind of a nasty function. It depends on both your X and your Y position. But for anywhere in this Cartesian plane, right, if we define our Z-axis as being along the dislocation line, anywhere in this plane, we can write what our stress is at a given point, right? And notice a couple things about this, if you don't recall or you've never seen it before. We've got a x squared plus y squared, so that means in the numerator. So the numerator is going to grow faster than in the denominator again. The denominator is going to grow faster than the numerator. So this will fall to 0 at infinite distance. But at distances the size of a grain, in a fairly fine grain sample, the stress fields can actually extend from one side of the grain to the other. Right? So we can begin to approximate the stress field of a grain boundary by taking our periodic array of edge dislocations and thinking about the slip plane. So we're taking the shear stress on this slip plane at distance, some distance x to the right of this dislocation here. All right? And from our previous slide, we have it here. And then we can calculate it for all these dislocations above and below the slip plane. Right? It's not that hard to write out. So for the second dislocation, right? If we plug it in, we get this. In general, we replace the 2 with an n here. And we can essentially sum it up from negative infinity, negative y, to plus y. All these different dislocations. And we've got a infinite series here. And it turns out this is actually a convergent series. And if you look in your classic dislocation texts, you get a solution for it. So this gives the stress field as a function of the distance from this grain boundary. What's important is it has all the things that we think about it. Shear modulus, Berger's vector, Poisson's ratio, the things that are in the stress field of the dislocation. But here we see it depends on distance squared times this hyperbolic sine term. And for those of you who were really good at functional analysis, will know that this drops off much, much faster than the stress field for a single edge dislocation, right? So it seems kind of counterintuitive at first in that an array, a cluster, a group of dislocations can put themselves in such a way that they actually have the stress fields superpose to a much smaller stress field than if it was a single dislocation. You were the same distance from a single dislocation. Right? It's not immediately intuitive when you think about how the atoms of a dislocation are arranged that this would actually happen. Right? So basically, what we can say is that by the time we're 25 Berger's vectors away from a grain boundary, we're in a zero stress configuration, right? So that means 25 atomic distances away from the grain boundary, there's no stress, right? Compare that to the stress decay for a single edge dislocation, right? Right? And of course, it also depends on, right, this is just a blow up here, right? But you can see this is the critical resolved shear stress calculated. So you can see that even a fair number of atoms away from a single edge dislocation, you still have a stress field that's still relatively high compared to the critically resolved shear stress, right? And this is really important when we think about strengthening, how these dislocations interact inside the metal. Okay. Yeah. Okay.
So the shear stress in MPA, very close to the grain boundary, is very high. It's close to and that's
yes. Okay. So let's take them one at a time, right? So notice that the calculated stress of a single dislocation also goes to infinity as it goes to zero, right? So that's a problem with our derivation, right? It's a numerical artifact, and the way you get around that when you calculate the energy of a dislocation is you ignore the region that's highly distorted near the dislocation line that we call the dislocation core, right? We'll talk about core effects in a bit. So we typically, when we need to integrate, we go some distance away from the core and integrate out and then say, the core contributes about 10% of the total, right? And it's some kind of made up hand wavy number. That's another really important open area right now. And something that Professor Ghazi Saidi works on very much is understanding the core structure of dislocations through atomistic simulation, right? So I don't want to necessarily head down that rabbit hole here. So the first part, yes. The second part where you say the stress is significantly higher than the yield stress, that's because we're being a little fast and loose with the definition of stress when we're at the atomic scale. Stress is inherently a continuum concept, right? So we can talk about strain at the atomic scale by meaning displacements of atoms. And we can have forces that act on those atoms. But even though lots of people say it, it's not entirely, I have a huge problem actually, with talking when people define stress at the atomic level, right? So what we're doing here with these equations is we're taking continuum scale calculations and interpolating them down to levels where we're talking about a handful of atomic distances, right? And so when we talk about the yield stress or the critically resolved shear stress, we're talking about the macroscopic stress resolved onto the slip plane along the slip direction, right? And it's the force of the available to push a dislocation along, right? It is significantly lower than the theoretical yield strength, right? Which would be what you need to shift entire planes of atoms next to each other, right? The reason we can have stresses much higher than that is because there are no dislocations to move, right? Right? The stress field from a single dislocation is balances, right? A dislocation can exist by itself, right? So it's in balance, it's under equilibrium, so it's not moving under its own power. If you had two dislocations and you smashed them close to each other and they were of opposite sides, they would spring apart under this motion. So the stress field can be significantly higher than the resolved shear stress, but significantly lower than the cleavage theoretical strength of the material. Going to infinity is an artifact of doing continuum calculations at super small length scales, right? But it's just there essentially to show that these forces that are acting on atoms near dislocation can be very significant, right? So thanks for asking. Okay, so if we know that there's no stress field unless you're very close. But we also know that grain boundaries have an energy. Right? There's a defect structure. All of those dislocations have an energy associated with them, right? So what kind of energy do we get together happens when we put a whole bunch of defects together to make an interface, right? So again, here we have to start with the energy of a dislocation, right? It's not hard to derive for a screw dislocation, right? We know that we get the strain energy density is GB squared over R squared, the distance, right? R is because you ever forget something so simple? What? Yeah. All right, so this is the rule of thumb here, right? Right? So the shear strain depends on the radius away, right? And so this R squared it's not the energy, it's the energy density. So it's the energy density at a point at given R, right? Again, continuum mechanics concepts. This is like my bread and butter, and I'm really embarrassed that I looked at this and just blanked for a second. Right? It's not this. We're not talking about strain energy. This is strain energy density. So strain energy per unit volume at some distance away due to a screw dislocation being at the origin, right? The strain energy for an edge is pretty much the same, except it has the Poisson's ratio correction in there. But the important thing is this is going to be the energy of a dislocation is proportional to GB squared. Right? So we want to calculate the energy of a grain boundary. So here we do something a little bit differently. I'm not going to go through this derivation very carefully at all because it's kind of long and nasty. Look it up in Herfenlothe. But the main idea of this is what we want to get out. So I don't care about you understanding law. It'd be great if everyone went through it once to understand it. But I'm never going to ask you to do it. Right? The thing I'm going to ask you is the end result that we're going to get to. And I'll highlight that end result. So if we start with here two infinitely long parallel grain boundaries that have some distance apart, but all of these are on the same plane. So on each plane where there's a positive edge, there's also a negative edge on the same plane a distance away. All right? So if you bring these together to some distance where the distance is small enough that their core energies cancel each other out, right? You've got a structure that's up and one that's down. If you bring them in close enough, there's some theoretical distance. Their core energies cancel each other out. And then I start from those infinitely close together dislocations, and I calculate how much energy I need to put in them, the work done to separate them so that they're infinitely far apart, right? So I integrate the work done over a huge distance, right? This is going to approximate the interaction energy for those pair of dislocations, right? Because conceptually, does that make sense? Right? I take two defects, I shove them together, and then I say the strength of their interaction is going to be how much work I have to do to separate them apart so that they're not interacting anymore. Right? Okay. So now if we consider that we do this for the entire interface, I move the two interfaces close together and separate them apart. Right? We now have the interaction energy of those grain boundaries. Right? We can also do it one at a time. Right? We can essentially take two individual. Right? We can take the negative dislocation from the boundary. Right? Take one, move it in, move it out, and integrate from R0, which is where their core energies cancel, out to here. This becomes the shear stress on the interface. The shear stress on the energy per unit length of the dislocation. Right? We do some substitution. Oh, something's not right here. There's a typo somewhere. I'll have to go in and look at it because here we multiply by 1 over d. So this gives us the energy per unit length of a dislocation, right? To get to grain boundary energy, which is per unit area, I need to multiply it by 1 over d, which is my separation between the dislocations. And you can see here, if I have a d down here, and I multiply it by 1 over d, I should have d squared. But I know in my final result, I shouldn't have a d. So there's something wrong with this equation, right? So I made there's a typo here. I'll have to sort that out. But anyway, by looking at the interactions between these two dislocations, we can get the energy per unit area of the boundary as an approximation. And because we're assuming small angles and all that, we can come up with a form that sort of looks like this, where this alpha parameter depends really on the core energy, right? And if we look at the calculation you get from this, this is the Shockley-Read formula. You can see that it's small at zero. Of course, at zero misorientation, low angle grain boundary, we have zero interaction energy because it's just a perfect, right? It's a perfect crystal. There's no interface, so the interface should have zero energy. As we increase, we go to higher and higher energies until we're in the high energy regime, and then it basically flattens out until we get to another symmetric equivalent. All right? So you can tell this is not for FCC because we talked about, right, in FCC the maximum misorientation, the cubic misorientation was out here. Right? So this is, have to think about it as to what kind of crystal where you have 90-degree symmetries, right? So just think about that for a little bit. So this is the calculation that you get, this dotted line. The experimentally measured grain boundary energies look like this. What are these deep cusps? These are for things, grain boundaries that are particularly well aligned, like twin boundaries. In FCC, if I take my 111 axis, and I do 120 degrees about 111, that's a symmetry element, right? Threefold rotation about 111. If I go halfway around it, 60 degrees, right? I'm at a position where a huge number of my atoms line up nicely, right? It's a very low energy structure, right? If I deviate just a little bit from it, it spikes back up. So if you look at the energy, grain boundary energy as a function of misorientation for FCC, you see there's a really deep cusp right at 60 degrees. That's because of the special twin boundaries, annealing twins, and all right. So the real grain boundary energy is not a nice, smooth, monotonic function like our approximation is, right? But generally, the end result of the analysis is that general high angle boundaries have higher energy than low angle grain boundaries, and that's predicted by the Read-Shockley analysis. But in reality, things are complicated because we actually have a whole bunch of low energy structures. And it becomes even more complicated because once your system is close to a low energy structure, it doesn't take a lot there's a huge gain from rearranging yourself to actually get to the low energy structures, right? So we can tell if we're doing, say, EDSD, and we measure a 60 degree about 111, we can be pretty sure that those are twins, even though we can't see the grain boundary plane from a 2D section. But it's just the fact that the system is so well optimized at that location that any grain boundary plane direction, right, it's going to the system is naturally going to evolve to that. Yeah.
Previous, like at first you say that we have twisting between two grain and we have tilt. So we have edge dislocation and screw dislocation.
Yeah.
So but here just you use edge dislocation.
This is a huge approximation. Right. Right. This is right. This was done in 1950, before this was all done, hand calculations, right? So people had to come up with models for the grain boundary, right, energy that could be solved analytically, right? So if you do actual atomistic calculations, you can calculate the energy of an arbitrary grain boundary, right? And that space is huge, right? So there's a lot of assumptions in this model that give us some general trends, right? And those general trends are important, right? What are the consequences of this, right? Which is going to be harder to move? If you anneal it, are you going to get rid of sigma 3 interfaces? Are those grains going to grow? Are those interfaces ever going to move? If I have these special, no, they're low energy boundaries. They're perfectly flat, planar, low energy boundaries. They're not going anywhere. The rest of your system will evolve around them, and they'll stay right fixed where they are, right? Because the other grains, the other interfaces are going to be these general high angle grain boundaries out here, right? Low angle interfaces are much lower energy. They're much more stable in your microstructure, right? So we can use this knowledge to do things. We can if we can process our material in certain ways to generate low angle grain boundaries in twins, we can have much more thermally stable microstructures, right? This is things that people that are really involved in grain boundary engineering are doing, right? That's like one of their main research focuses. Is how do I process my material to get grain boundary populations that I like, that give us the property? So Ben's telling me it's time. So the last slide for today is just looking at that alpha parameter, the core energy. So the core structure of the dislocation is very important on the grain boundary energy, right? So this is an intrinsic property, right? So this is essentially where you get that the grain boundaries energies in different metals are going to be different because of the spacing and the core structure and the core energy of those defects are going to be different, right? So we'll stop there. We'll talk about surface tension and other grain boundary properties on Monday.